Hey everyone, Dan Mason here, and today we're diving deep into the scientific method, questioning it in a manner that's as rigorous and systematic as the method itself. Now, before you grab your torches and pitchforks, understand this. Questioning the tools we use to understand the universe isn't about tearing them down. It's about making them better. Think of it like upgrading your telescope. You're not tossing it out the window because it's flawed. You're refining it to see even farther, even clearer. That's what we're aiming for today. A sharper, more robust understanding of how science itself works.
Before we can scrutinize a structure, we need to examine its foundation. The scientific method, for all its power, rests upon certain assumptions. First, it assumes that the universe operates according to consistent laws, that the same causes will produce the same effects, whether we're talking about apples falling from trees or galaxies colliding in the vastness of space. Secondly, it assumes that these laws can be understood through empirical observation, that our senses, aided by instruments, can provide us with reliable data about the natural world. But are these assumptions always valid? Can every phenomenon be neatly boxed into cause and effect? What about complex systems, where emergent properties arise not from simple linear relationships, but from the intricate interplay of countless variables? And what about the observer effect, the very act of observing a phenomenon influencing the phenomenon itself, particularly in the quantum realm? Furthermore, the scientific method relies on the reproducibility of results. An experiment conducted in one lab should yield similar results when replicated in another lab, 1,000 miles away, using the same methodology. But what if subtle variations in environmental conditions, undetectable biases in researchers, or even the sheer complexity of the system under study introduce variability? These are not mere academic questions. The history of science is littered with examples of theories, once considered rock solid, crumbling under the weight of new evidence or more refined methodologies. Remember, even Einstein's masterpiece, the theory of general relativity, initially faced resistance.
Throughout history, there have been moments where the scientific method, at least as it was understood at the time, led to conclusions that, in hindsight, appear tragically flawed. Take the example of phrenology, the now debunked practice of determining personality traits and mental faculties by analyzing bumps on the skull. While seemingly absurd today, phrenology gained significant traction in the 19th century, bolstered by its seemingly empirical approach of observation and measurement. However, its downfall lay in the flawed assumptions upon which it was built, namely, that the shape of the skull directly correlated with brain structure and function. Similarly, the theory of spontaneous generation, which posited that life could arise spontaneously from non-living matter, held sway for centuries, supported by observations of maggots appearing on decaying meat. It took Louis Pasteur's ingenious experiments, using swan-necked flasks to control for contamination, to demonstrate that life only arose from pre-existing life. These examples highlight the critical importance of rigorously questioning the assumptions underlying our scientific inquiries, and recognizing that even the most carefully constructed methods can be susceptible to biases, limitations, and the ever-present potential for human error.
How do we design experiments to probe the very limits of the scientific method itself? One approach involves exploring areas where the scientific method traditionally struggles, such as consciousness or the subjective experience of emotions. Imagine an experiment where we attempt to quantify the feeling of love. We could measure physiological responses like heart rate, blood pressure, and brain activity. We could even analyze hormonal changes. Yet, can these objective measurements truly capture the subjective, qualitative essence of love? Another avenue involves exploring systems of such immense complexity that traditional reductionist approaches, breaking down problems into smaller, more manageable parts, prove inadequate. Take climate change, for example. While we can study individual components like greenhouse gas emissions, ocean currents, and atmospheric circulation patterns, the interconnectedness of the Earth's climate system makes it challenging to predict with absolute certainty the long-term consequences of our actions. These challenges don't invalidate the scientific method, but they do highlight the need for humility, for acknowledging the limitations of our current understanding, and for continually refining our methods as we grapple with the universe's most perplexing questions.
Data, raw and unprocessed, is like a jumbled jigsaw puzzle. It's only through the lens of statistical analysis that we begin to discern patterns, to separate signal from noise, and to draw meaningful conclusions. Statistical tools allow us to quantify the uncertainty inherent in any experiment, to determine the probability that our results occurred by chance, or to identify potential correlations between variables. However, even the most sophisticated statistical analysis is only as good as the data upon which it is based. Biases in data collection, flawed sampling methods, or even the misapplication of statistical tests can lead to misleading or downright incorrect conclusions. Furthermore, we must be wary of confusing correlation with causation. Just because two variables appear to be related doesn't mean that one causes the other. There could be a third, hidden variable influencing both. The takeaway here? Statistical analysis is a powerful tool, but it's not a magic wand. We must wield it with caution, understanding its limitations and interpreting its results within the broader context of our scientific inquiry.
In the world of science, our work doesn't end with a triumphant eureka. It faces the scrutiny of our peers, experts in the field who dissect our methodology, scrutinize our data analysis, and challenge our interpretations. This process of peer review, while sometimes grueling, is the bedrock of scientific rigor. It acts as a filter, weeding out flawed studies, identifying potential biases, and ensuring that only the most robust findings make it into the scientific literature. But even peer review isn't foolproof. Reviewers are human, prone to biases and oversights. That's why replication, the ability of other researchers to reproduce our findings independently, is paramount. If a finding can be consistently replicated across different labs, using different datasets, and even with variations in methodology, then our confidence in its validity grows exponentially. Conversely, if a finding proves difficult or impossible to replicate, it raises red flags, prompting us to re-examine our assumptions, our methods, and our conclusions.
Science isn't conducted in a vacuum. It's shaped by philosophical assumptions, by our understanding of what constitutes knowledge, truth, and the nature of reality itself. Philosophers of science, from Karl Popper to Thomas Kuhn to Paul Feyerabend, have grappled with the limitations of the scientific method, questioning its objectivity, its ability to truly capture the complexity of the natural world, and its relationship to other ways of knowing. Popper, for example, argued that true scientific theories are those that are falsifiable, meaning they make specific predictions that can be tested and potentially disproven. Kuhn, on the other hand, emphasized the role of paradigms, overarching frameworks of thought that shape how scientists interpret data and conduct research. These philosophical perspectives remind us that science isn't a static, monolithic entity, but rather an evolving human endeavor, constantly refining its methods, questioning its assumptions, and pushing the boundaries of our understanding.
To truly test the strength of an argument, we need to subject it to the most rigorous counter-arguments. What are the criticisms leveled against our exploration of the scientific method's flaws? Some might argue that by highlighting limitations, we're giving ammunition to those who seek to discredit science, to peddle pseudoscience, or to sow doubt in the face of overwhelming evidence. However, acknowledging limitations isn't a sign of weakness. It's a mark of intellectual honesty. Others might contend that the scientific method, despite its flaws, has a proven track record of success, leading to countless discoveries and technological advancements. And they'd be right, but that doesn't mean we should rest on our laurels. Just as a smartphone today makes a flip phone from the 1990s look positively archaic, our scientific methods of tomorrow should make even our most sophisticated tools of today seem rudimentary by comparison. Questioning the scientific method isn't merely an intellectual exercise. It has real-world implications. It forces us to confront ethical dilemmas, to consider the potential consequences of our research, and to ensure that our pursuit of knowledge aligns with our values. For example, as we develop increasingly powerful artificial intelligence, how do we ensure that these systems are aligned with human values? as we delve deeper into the complexities of the human brain. What ethical considerations guide our research and its applications? Furthermore, recognizing the limitations of the scientific method can spur innovation, leading to the development of new tools, methodologies, and ways of thinking. Perhaps we need to move beyond reductionism, embracing more holistic approaches that consider the interconnectedness of complex systems. Ultimately, by acknowledging the flaws inherent in even our most cherished tools, we open the door to refining them, to forging new paths of inquiry, and to ensuring that science continues to illuminate the mysteries of the universe for generations to come.
So, is the scientific method flawed? Absolutely. But that's not a condemnation. It's an invitation to improve, to refine, to push the boundaries of human understanding even further. By following these steps, we can question the scientific method in a manner that is itself scientific, contributing to the ongoing refinement and evolution of scientific inquiry. Remember, science isn't about dogma. It's about curiosity, skepticism, and the relentless pursuit of truth. It's about embracing uncertainty, acknowledging our limitations, and constantly striving for a more complete and nuanced understanding of the universe we inhabit. Let's continue to explore, to question, and to marvel at the wonders that science reveals, even as we recognize the imperfections of the tools we use to unveil them.